Okay, morning. Yeah, I brought my microphone. I think the sound quality should be better now. Yeah. So let's finish the complex number, and then we'll start this second order ODE. Okay? Yeah. So just a quick review. Euler's formula. E to the power of j theta equal to cosine theta plus I sine theta. E to the power of j omega t if you change the theta to omega t, and I'll just cosine omega t plus I sine omega t, right? Okay, so that's Euler's formula. Now you can try some of the special angles here. For example, what is EG pi? Right? What does EG pi equal to? So if you plug this pi over here, so it's cosine pi plus I sine pi. And I sine pi is 0, and cosine pi is -1. So you have this guy equal to 0. So a lot of time, if you do a little search as to Euler's formula, as a matter of fact, what they give you is some of the they give you this guy here. See, Euler's formula is e to the power of I pi plus 1 equal to 0. So where's that from? It's basically from here. Okay, yeah. So we also started on talking about the phasor. So the application of phasor, it basically is mainly on the AC circuits, and also to deal with this sinusoidal kind of signals. So if you have a sinusoidal signal right here, okay, and instead of processing this sinusoidal as it is, we consider it as a part of this complex number. So that's why we call this v of t is the real part of this complex number here. Okay, and inside this big bracket, that 8 multiplied by e to the power of j phi, and that's what we call the phasor. Okay, this is the phasor for this v of t here. Okay, yeah. So dealing with this one here a lot of time proved to be simpler than directly using this. All right, so now just a little bit further here, and the Euler's formula, there's one little thing that might be useful is this. So you see this is Eg theta equal to this, right? How about E negative j theta? So basically we change the theta to cosine to negative theta. So I'm using I, right? So I guess I will change it back to j. Okay, so this is cosine negative theta, sine negative theta. And as we know, cosine is an even function, so this is cosine theta. Sine is odd, so this is negative sine theta. So that's what e to the power negative j, let's change this to j here, because I use j at here. Right, so that's what e to the power negative j theta is. Okay, so now I'm going to do this, okay? So here is the e to the power j theta, and this is e to the power negative j theta. So I'm gonna add these two together, okay? Add these two. So if I add this and this, so 1 plus 2, okay? So what do I get? I have cosine theta plus cosine theta, I have positive this plus this negative this, so that canceled, right? So I got basically Ej theta plus E negative j theta equal to 2 cosine theta, and which give me this cosine theta equal, okay, Ej theta plus E negative j theta over 2. Okay. Yeah. So that's that's one way of actually finding cosine theta. One of the bonus questions in the latest assignments, want you to prove something like sine 4 theta equal to something, I think, right? And that's actually where you can make use of this kind of a quantity right here. So similarly, if you use 1 minus 2, and you're going to get sine theta equal to Ej theta minus E negative j theta over 2j. Okay, you're going to get this guy here. Okay, so that's one thing we find here. And one more thing is this. So sometimes what you're going to do is you probably is this. So let's see. This is what we call the nth power. Okay, nth power of a complex number. So if I have a complex number z equal to a plus jb, okay, z equals a plus jb, that's a complex number, right? So what you may require to do is, what's the z to the power of 4, for example, right? Or what's the, in general, what is z to the power of n? Okay. So what would you do? You technically, very traditional way of doing this is, if you're calculating z to the power of 4, and what you're going to do is a plus jb multiplies a plus jb multiplied a plus multiplied 4 times, right? So you expand those factors by 4 times, essentially. Okay, so that you can imagine, if the number n is bigger, it's going to be very tedious kind of work, right? Yeah, unless you're a computer. Now, however, the other way of doing this is, so if I convert this one, because remember, complex number, we have different ways of expressing complex number. This is the first kind, and the other kind expressing complex number is what? Is this, right? Is this. So I can express complex number using its a magnitude r, also called actually so-called modulus, right? Yeah. And the other one is the argument. So I can use this one to express this complex number. Now, if I'm trying to calculate this nth power of the complex number, see what happens, right? If I say z to the power of n, then it's equivalent to saying this guy to the power of n, okay? And this guy to the power of n, so there are two basically quantities. One is r, the other is e to the power of j theta, and that's basically r to the power of n and e to the power j, what? N theta, exactly. So you see, that's much simpler, right? And one step, you end up with this result here, okay? So then, if you're required to find this, what the complex number is, you can simply write it back and say, oh, this is r to the power of n using Euler's formula. This is cosine n theta plus j sine n theta. Okay? And use your calculator to calculate cosine n theta or sine n theta. That's what you get for this nth power of the complex number. Okay? Yeah. So this transformation, this kind of a different perspective of computation, a lot of time can save you this computation time, right? Okay. So that naturally brings us to the next question here. This is the nth power of a complex number, right? So the next one is called the nth root of a complex number. Okay. Nth root of a complex number. So what's nth root? If I just talk about the nth root, not a complex number, huh? Let's say I have I have a number 4. If I have an x equal to number 4 here, okay, that's a real number, right? And then when we see that, what's the square root, right? We will often talk about square root of x equal to 4. So what do you get? Square root of x equal to 4 should give you a 2, right? Well, actually, positive, negative 2, right? The reason because square root of this, basically the power of this give you back this 4, right? The power of this give you back to 4. So we call this positive negative 2 is the square root of 4 here. That's purely talking from a real domain here, right? Yeah, real domain. Okay. Yeah. So if this is a negative number, x equals negative 4, and you don't have any real square roots, basically. Right? Yeah. So now we're going to talk about this nth root concept for a complex number here. Okay. Yeah. So consider a complex number. First of all, this is a complex number to consider, and instead of considering the complex number in this, I'm going to consider the complex number in this format here. Okay. So consider z equal to Rej theta. Okay. So what we're going to look for is we look for a w. Okay. We look for a w here. So the w here is also going to be a complex number. So I'm going to express this w using another set of a parameter. Okay, so this is another set of parameter rw theta w. Okay, for w right here. So we look for this w such that this w to the power of n, equal to z. Yeah, see the logic here, right? So if you compare to the real case here, so what's the difference? Actually, the idea is the same thing, no difference, right? So here's positive and negative 2 is a square root, so that to the power of 2 is 4, right? It's 4. So now we're looking for a complex number w, and that w to the power of n equal to z. Then this w is called nth root of complex number z. Complex number z. So that's the definition of nth root of complex number z. So w to the power of n gave you back this z. Is it clear? Okay, so that's the objective. Okay, so now let's come back to this one here, right? So this is the constraint here we're going to have to make use of. Okay, so what is the w to the power of n, right? Let's see. What's w to the power of n first? Here's the w we're looking for. Suppose you have the w, right? Suppose you have w. Then the w to the power of n, this is exactly what we just talked about, the nth power of a complex number, right? The nth power of a complex number. So then w to the power of n, according to what we just find it out, you can use this format, Rej theta format. So this is basically Rw Ej theta w to the power of n, right? To the power of n. So that's basically Rwn Ej n theta w. Okay. And what we want is we want this guy to equal to this given z, right? We want this one to be the z here. So we want this Rwn Ejn theta w equal to z. Okay, z is given. Okay, z is given, and z is given. So z is this guy here. Z is this guy, and z is Rej theta. Okay, Rej theta. Okay, so that's pretty simple now. You want this one to be the same as this one here. So basically this quantity has to be the same as this quantity, right? And this n theta w quantity has to be the same as this theta at here. That makes sense? Yeah. So that basically give me, first one here, Rwn equal to R. Okay, Rw equal to R. And that basically means this Rw equal to R to the power of 1 over n. So now we found what the Rw is, right? So we're trying to find Rw. We're trying to find a W satisfying this constraint in here, this relationship. And the first requirement is this magnitude or the modulus of the W complex number has to be this r to the power of 1 over n here. Okay. The second quantity here, this is n theta w, okay, equal to theta, right? Equal to theta here. Okay. Now, however, okay, because of the unique things of this ej theta, what is ej theta? Ej theta is cosine theta plus j sine theta here, right? Yeah. So what's the unique about the cosine theta, sine theta? They are periodic, right? They're periodic. And what's the period of this cosine theta, sine theta? 2 pi, right? It's 2 pi. So basically, if you have a cosine theta plus any integer number times of this 2 pi, this guy doesn't change, right? So basically, cosine theta equal to cosine theta plus what? 2k pi, right? Okay. So now, instead of saying here, this instead of this just a theta here, I'm going to change that theta to, I want to change the theta to 2k pi, okay, 2k pi here. Okay. So what's the k here? K is 0, 1, 2, could be any numbers, okay, could be any number, could be any integer numbers here. Okay. So then this way here, this n theta w will be simply, okay, theta plus 2k pi. Okay. Any questions? Okay, so based on this expression in here, you have theta w, right, equal to this theta plus 2k pi over n, okay, over n. So there we go. So these two quantity, right, is what we're looking for. We're looking for what? We're looking for the w satisfy this equation. And that means this rw and theta w, which is a quantity, define this w here, has to satisfy this for these two expressions in here. Right? So that's basically how we find this w. Okay. So now let's take a look at example. Let's see technically what does it mean by this nth root? Okay. Now technically, if I write it back, my w, right, will equal to rw. That's going to be basically r to the power 1 over n multiplied by cosine theta w, which is this guy here, plus j sine theta. Okay, so this is what the w here, right? This is what the w is. And the k is 1, 2, up to, okay? So k, yeah. So k technically could be any integer numbers here, right? Could be any integer numbers. However, okay, if I look at this k at here, okay, so you see what happens is inside this bracket here, okay, let me write down one more step here. This is theta over n, 2k pi over n, and j theta over n, 2k pi over n. Right? So this is what inside this bracket here. Okay, so we know that we understand that the cosine and sine are periodic function, and their period is 2 pi. So basically, this is now the theta. This theta is theta over n. So if this guy is a 2 pi, and it's not going to change, right? Not going to change. Basically, come back to this one here. So then what happens is, see, that k, when you increase from 0 to 1 to 2, and then up to n minus 1, everything's fine. And then what happens when k equal to n? This quantity becomes, when k equal to n, this quantity becomes what? 2 pi. So basically, that come back to a loop now, right? They come back to this loop, okay? Yeah, to the origin of the loop. So your k doesn't have to go beyond n minus 1, right? Your k just have to stop at n minus 1. If you go beyond n minus 1, you're just basically repeating the loop, right? Because periodic things. Makes sense? Yeah. So this is what the case range is here, okay? Yeah. Okay, so let's look at an example. I want you to find the fourth root okay, for z equal to -1, okay, z equal to -1. Yeah. So fourth root of z equal to -1. I think what's your first, when you look at this question here, what's your first confusion? Huh? It's a real number, right? It's not a complex number. Well, again, what we had to emphasize, complex number is a bigger domain here, right? So this z equal to appear to be a real number, but it's actually still a complex number. It's just what? The imaginary part of the complex number is 0. Okay? Is 0. Yeah. So the first step is, what we need to do is, right, if you look at the process I just did it here, the first step is I need to express my complex number into this format here, right? I need to express it into this format. re to the power of j theta. Okay? So then this is a z equal to -1. So for this particular one here, what do I need to do? Okay, first step, okay, if you're not quite familiar, draw or sketch this z equal to -1 on the complex plane. So this is -1 over here, right? It's -1 over here. Okay. Then find the corresponding r and a theta associated with this complex number z equal to -1. Okay. So tell me what's r and what's theta? R is what? 1. Theta is? 0? Pi. That's right. Yeah. Here is the complex number, right? From the horizontal axis to where it is, that's the theta angle. So that's theta is pi, okay? Yeah. And you can always verify. So your z equal to ej pi. Is that really the case? Actually, that's the case. I think that's the case I was going over at the beginning of the lecture, right? So this first one is 1, the second one is 0. Okay? Yeah. Okay, so here is the complex number. Now we're trying to find the nth root of complex number. So as a matter of fact, okay, what you need to do is, if you don't remember the formula, okay, you can simply go over this process. You can easily derive this formula here, okay. But in the past, I think I've been able to give you the formula here. But one thing amazed me is, you know, I can tell you, I will test kind of this kind of case in the final exam, okay. But however, no matter how many times I say it, you know, even if I give you exactly this same example at here, okay, out of 170 students, I probably will have maybe more than half who couldn't do this example here. Now you got to ask yourself, if I give you this exactly the same thing, okay, will you be able to repeat this example here? Right? So, no, okay, not exactly the same thing. Maybe not a -1, maybe just negative some other numbers, right? Yeah, pretty much the same thing. Okay, so now I'm going to find my W here. So I'm going to just go over and make use of my formula here, okay? Yeah. So r to the power 1 over n, that's just 1 because r is 1, okay? N here is 4, okay? N is 4, so r over 4, that's 1 here, okay? Yeah. And my W, basically just, if I go back to my formula for W here, this is my W. So my W will be cosine theta, right? In this case, my theta is pi over n, which is 4. Okay, like this. This is W here, right? This is W. Okay, according to this formula. Okay, yeah. And what's the key value? That'll be 0, 1, 2, and 3, right? So up to n minus 1, up to this 4 minus 1, 3. Okay. So you have how many? You have basically 4 roots, right? 4 roots for this complex number. Okay. Remember what's the meaning here, right? I mean, remember the meaning is w to the power of 4 equal to z. Okay. In other words, z here is -1. So w to the power of 4 should be -1. That's what we're looking for. Okay, what we're looking for. And coming back here, so now we have the formula. Now what we need to do is we need to plug in all these numbers here and find what exactly is each one of the complex numbers. All right. So W1 for k equal to 0, you plug in 0 right here, so that's cosine pi over 4 plus j sine pi over 4, which is ej pi over 4. All right. Yeah, ej pi over 4. And the next one, W2, okay, you plug k equal to 1 at here, okay, so I'll save myself a little bit, so that's going to be ej 3 pi over 4. And W3 is ej 5 pi over 4. And W4 is ej 7 pi over 4. Okay. So that's the four complex number, or the so-called roots, right, for this complex number z equal to -1. Okay. Okay. So actually, it's quite interesting. If I plot, okay, if I plot this four complex number on the complex plane, if I plot them out, okay, let's see, where are they? Okay. So you need to be very quick now understanding the concept of this one here. Okay, when people are saying, hey, e to the power j pi over 4, so that basically you're thinking this is a point on a unit circle, right? On a unit circle. Why is a unit circle? Because the r at here equal to 1, and it's on a unit circle, and with how much angle movement? With a pi over 4 of a degree of movement from the horizontal axis. So this is the horizontal axis, and after it rotates about 45 degree, and which is this one here. So that is your W1 in here, right? So W1. And W2 is 3 pi over 4. So 3 pi over 4, that's basically over here, right? And there's a 90-degree difference here. So this is W2. And W3 is going to be here. And W4 is going to be here. Okay. So this four complex number, W1 to 4, evenly dissect this unit circle, basically. It's like a 360 degree divided by 4, right? So separating by that, so then 90 degrees. Okay, yeah. Okay, so that's basically how you draw it. If you have a fifth root or sixth root, basically you're gonna have 5 or 6 and complex numbers around these unit circles. Okay, yeah. Not necessarily unit circles. If the z is not 1, if something else, it's gonna be a circle with a certain radius, right? Yeah. Okay, any questions? Yeah. Good? Yeah. Good. Complex number doesn't stop it here. You know, usually there is a dedicated course called complex analysis, right? So basically, in that kind of course, you keep going and you actually do derivative and integrals regarding complex numbers. So everything in complex domain, right? Yeah. Complex number is used for a couple of applications. One of them is what we're going to use for solving second-order differential equation. The other one is in control system. You analyze this, analyze the system frequencies. You're also going to use a complex number. And there's one more interesting thing here is complex number is fractals. So just sort of touching on it here. How many of you know what fractal means? Yeah. So fractal basically is a sort of a pattern. It's a self-similar pattern, right? Self-similar pattern essentially. Let's say when you have a cauliflower, right? You know you have the cauliflower there, and do I have a cauliflower? I thought I know I don't have it. If you look closely, right, you know, overall picture, overall it's that kind of shape. But then if you do the cooking and you cut each one of the branch, each one of the branch is pretty much the same as the whole cauliflower, right? But if you look even deeper into it, the smaller ones, and they're still the similar pattern as this each one of the branch. So that's what we call the self similarity here, Well, in philosophy, there is a saying, there's a universe in every drop of the water, in every grain of the sand there, right? So that's what we call the self-similarity, right? You look beyond this big, and you look deep into the smaller ones, microscopic scale. It's actually look like it's the same pattern and same shape, right? That's basically self-similarity. And some of the research nowadays, if you know that you have probably heard it, it's called MEMS, right? A microelectrical mechanical system. So what it is they basically shrink the scale of the regular mechanical system or electrical mechanical system into very, very, very small scale, right? You have a gyroscopic sensor, and it used to be this big, and now they shrink it down to this micrometer of scales there. Right? That's basically self-similar patterns there. And that's actually just essentially the concept of the fractals, right? Fractals here. Now, in complex number, you actually be able to construct this kind of a shape. So one of the very famous way of constructing this fractal is so-called Julia set. So what happens is you do this. Okay, this is what Julia set is. So you have a sort of an iterating expression here. So Zn minus 1 equal to Zn to the power 2 plus C. So the C at here is a constant. Okay, C at here is a constant. And constant means you give the C a certain value. You can give the C any values you want, okay? But not all value will produce the beautiful fractals. Some values doesn't. Some values are working better. And the Zn at here is a complex number. So you start this iteration with a certain kind of a complex number here. So you start with any complex number you want. And the C at here, by the way, not necessarily just a real, it could be a complex number too. Okay. So then you start this iteration, you get a whole bunch of basically Z, right? Depends on how many iterations you do, you get basically Z there, right? Yeah. So then what happens is, what you can do is, you can basically get the magnitude of each one of this complex number, okay? Just get the magnitude of each one of the complex number, and then you draw this magnitude, you draw according to the magnitude, okay? You draw according to the magnitude, use a certain color. So let's say 3, 4, so the colors will be different, right? They're different. And then you look at the pattern, basically, what's going to be if you have maybe a very large number, 500, 1,000, even more, right? That depends on your computer here. So that's what you're going to find here. This is only running for how many? This is only running for 20 basically iterations, right? Only 20 iterations. So then you end up with a kind of shape like this one here. And because the 20 is a very small number, right? It's hard to, the resolution is not good. But however, if you run bigger iterations, and if you zoom in into each one of the corners here, right? They have this similarity pattern here, okay? So they resemble like these parents, mother and father, basically, okay? Yeah. And in this particular case, I think the number I tried here is negative 0.745429. Don't ask me where this is from, but just kind of trying and errors here. Yeah. And if you can try some other numbers, you can try complex numbers, you will be able to come up with an absolutely different kind of a drawing at it here. Sometimes it's just stunning. It's actually stunning. Yeah. Some people used this concept here to construct this the face of the people. Yeah. So not sure how to realize, but it's doable, right? Okay. So if you're interested, just go ahead and read some of the things here. This is Julia set. Now it is C is constant. If you keep the C as a variable here, not a constant, it's going to be called a Mandelbrot set. Okay. All right. So just on the side of this complex number there. Okay, so any questions? Okay, good. Okay, so now we're going to our new topic here. Okay, second order ODE. Okay, so we're ready to talk about second order ODE now. Okay. So this is a big topic. Okay, we're gonna have quite a few lectures that are here. Okay. So first of all, let's take a look at second order ODE, which is actually not that strange to us. We actually have derived, okay, so we actually have derived certain kind of a second order differential equation already. This is a mass spring damper system, and if you recall that the equation for motion for this one here is mx double dot plus bx dot plus kx equal to f of t, right? F of t. So this is second order here, and this is second order ODE. It's actually linear, right? In this case, this is linear. Why is it linear? Because again, it satisfies the standard form, right? So it's a standard format. And it's time invariant if m, b, k are constant numbers. Okay, if they're not constant, it becomes a time variant system. So similar, you can have a second order ODE for RLC circuit, right? RLC circuit. Okay, so the whole point here is when you have such kind of ODE, so how do I solve for x? Right, that's basically the objective. Let's see, x is function of t here, right? How do we solve for this one here? Okay. Now, before we talk about how to solve this one, we have to lay down a few theories, right? Yeah. First thing is, I'm gonna write a looking at this one here. I'm gonna write a general second order ODE probably. Okay. So in general, the format of a general second order is y double prime plus px y prime plus qxy equal to fx. Okay, so that's general. Okay, so let's suppose the independent variable is x. You can change that to t. Absolutely. Okay. Yeah. Okay, when you have this kind of a general one here, one of the special case, right? First is when fx equal to 0. Okay, so there's no external input to the system. Okay. So fx equal to 0. If this guy is 0 and this second order differential equation, and just like the first order, remember what do we call that when this guy is 0? We call that what? Homogeneous. So we're having homogeneous one here. Okay. So we have a homogeneous case. And what we're going to do is we're going to consider that this is a special case, and we're also going to consider PS, QS as constant here first, okay? So we're going to consider this PX and QX constants. So they are not variables, okay? So we'll consider them variable, but in this here, there's a special one. This is basically the simplest you can get. Homogeneous and constant coefficients at here. Okay? And of course, I guess we have a relatively, yeah. So we have a fx not equal to 0, yeah. Okay. So that basically gives us a non-homogeneous. Okay, it gives us a non-homogeneous one. Okay. Yeah. Now, in this particular case, we're going to consider either the two cases when they are constant, when they are not constant. Okay, so we're going to look at the different cases. But overall, just remember, you have this one is 0 and this one is not 0. Okay, the way to solve these two cases, okay, are slightly different. But the solution for this one need the solution based on this one here, right? Yeah. Okay, so now first concept is this. Okay. The first concept is general solution versus particular solution. Okay. So if I look at simply the wording out here, I guess you can tell them the difference immediately, right? Particular, well, that's just particular, right? It's only suit this case, this situation here. General, it's satisfy every different scenarios, right? And we're gonna look at this first simple case. Okay, use this one as example, for example. Okay, let's see. Here's what we're gonna look at this one here. Okay, yeah. So I'll give you one simple example here, and we're not gonna solve that, but let's put it on here. Okay, so let's say I have a second order differential equation homogeneous, which is this one. Okay, yeah. Now I'm gonna tell you is, okay, y1 equal to cosine t. Okay, y1 equal to cosine t is a solution. So I'm telling you this solution. If you don't trust me, how do you verify? What do? You substitute into this second order differential equation, right? So you can see cosine t substitute here two derivative. So first derivative negative sign, second derivative negative cosine. So negative cosine plus cosine is 0. So that's definitely right. And you can also see that y2 is sine t. That's also a solution. It's also a solution. So if you put it there, sine t, cosine t, another derivative negative sine t is negative sine t plus sine t is 0. And if you put 2 cosine t here, it's still a solution. Okay, right? If you put 2 sine t here, it's still the solution. Okay, so all of this one here, what we call them particular solution, right? All of this one here, we call them particular. Okay. So those are the solutions. Seems like those are solutions coming out of a certain set, right? There's a pool there, right? There's a pool, and you're just pulling out one out of the pool, and that's each one of them, right? So our objective is where's the pool? How do I find that a general expression for the pool here? Well, what I can tell you is if you let y phi, which is c1 cosine t plus c2 sine t, okay? If you have this one here, so what is this? It's a constant c1 by cosine t and a constant c2 by sine t here, right? Now this guy here, we'll be able to prove that this is a general solution. Okay, this is a general solution. Okay. So if you don't trust me here, you do the same thing. If you plug this, C1, C2 could be any numbers, so could be any real numbers here, right? And if you plug in this one here, actually it could also be complex number. If you plug this one here into this second order differential equation, you can easily verify that this y5 is a solution, okay? Yeah. And we can show that it's going to be a so-called general solution. Now you can see now why is it called a general solution here? Just by visual check here, it's not a very rigorous proof. But if I let c1 equal to 1, c2 equal to 0, I get y1, right? If I let let's say c1 equal to 2, c2 equal to 0, I get this y3. Okay. So this is sort of the big pool there. Okay. Yeah. So that naturally brings us this first theorem. Okay, this first theorem here. So the first theorem is if y1, okay, is a solution to y double prime plus pxy prime plus qxy equal to 0, homogeneous, okay, homogeneous. If y1 is a solution to this, okay, and if y2 is another solution, okay, so I got y1 and y2 are both a solution to this one, okay. Then, okay, the theorem number 1 saying, then this c1y1 plus c2y2 is also a solution. Okay. Yeah. How do we prove that? I think I'm going to skip the proof here. Basically, y1 is a solution, meaning if you plug the y1 here, that satisfies this equation, right? y2 is a solution, you plug that, y2 satisfy that, okay? Then we can basically combine these two equations together and find out that this is another solution, basically, right? Yeah, so I'm going to skip this one here. But you need to remember this simple fact here, okay? So you have a C1, you have a Y1 and a Y2, both are solutions. Somehow you find it out, okay? And then you make a combination of these two, okay? Just combination of these two. You could get another solution of this homogeneous second order ODE. That's what it means here, okay? Yeah. Okay, but you got to be careful though, huh? I didn't see that this. I said this is a solution, but I didn't see that this is a general solution. Okay, so we're not there yet. Okay, so be careful of this. We're just saying this is a solution. Okay, so before we reach that stage of general solution, okay, we need to give you one more theorem. Okay, theorem number 2. Okay, so let me just write it down here, and then we can talk about the theorem number 2 in the next lecture. Okay, so number 2 theorem is this. It has nothing to do with this second-order differential equation anymore. It's purely a mathematical concept here. Okay, so consider yourself, okay, a set, okay, a set of functions. Okay, consider a set of functions y1, y2, and up to yn. Okay, so you have n number of functions, which is set at here. Okay. Then I'm going to consider an expression k1 y1 plus k2 y2 plus kn yn. Okay, and consider this expression here. Let's call it number 1. Okay, number 1 here. So essentially, you multiply each one of the function with a constant k1. So k1 up to kn. Okay, they're constant. Okay, they're constant. I don't know what constant, but you multiply certain constant. Okay, yeah. Now, if k1 equal to k2 equal to kn equal to 0 is the only it's the only way to make number 1 equal to 0. I'm using very plain language here. If this guy, if all of them is 0, is the only way to make this 1 is 0. Is that clear? Yeah. So, you know, basically, maybe not the only way, right? Maybe this is 2 or 3, and you add them up, it's 0, right? It's possible. But, okay, under certain situation is, if this guy is all 0 is the only way to make it a 0, then, okay, this y1 up to this yn, this whole set, okay, this whole set of the function at here, what we call them is, we call them linear independent. Okay, linear independent. Okay. Now this appears to be a new concept, but it's actually not a new concept. Okay, not a new concept. So the idea is here is the independent here, right? So if you recall that when you're solving linear algebra matrix, you know, what situation gives you the determinant matrix 0? When under what? Under what situation you have a determinant matrix 0? Come again? The equations are what? You said it. When the equations are not independent, right? Basically, you have one equation here, you have another equation, and this second equation is probably the scale of this first equation, right? Or in terms of rows, the first row is the scale of the first rows, and then in that case, the matrix is not going to determine, not going to be 0. So that's the same idea here, okay? The same idea. Independency or dependency, basically meaning whether the y1 depending or not on the other ones. So we'll talk about in detail in the next lecture. Thank you.